Welcome to Unit 4, Lesson 1, Characteristics of Polynomial Functions. At the top here, you have some key terms that we're going to be using throughout this unit, and just get into it. So, the polynomial function. Polynomial function is a function in the form, and it's got all these letters here, but basically, if you look down here, here's some examples. So, n is a whole number, x is a variable, and the coefficients are real numbers. I don't know why that got in there, so just cross that out. Examples are, so f of x equals 2x minus 1, of course, is a linear function. F of x equals x squared plus x minus 6, of course, that's a parabola. And this one is a function to the power of 3, and we'll talk about the shape of that graph shortly. So there's some terms that go with polynomial functions that you need to be familiar with. The first one is end behavior. This is the behavior of the y values of a function as the absolute value of x becomes very large. So what we're looking at is as the graph goes off into infinity, either positive or negative direction, what is happening. So which quadrant is it ending in and what direction is it heading, and we'll talk about how to determine that shortly. The degree of the function, you just want to look at the highest exponent available. So for example, the degree of this one is 3, this one is 2. Oh, that's off the screen. The degree of this one is 3, this one is 2, and this one is 1. The constant term in a function is the coefficient which has no attached variable. So in this example above, of course, it's minus 6. The leading coefficient is in front of the variable with the highest power. All of these have a leading coefficient of 1, but you could potentially have a number in front of it, say 3x cubed or something like that. So whatever number is in front of the biggest one, that's our leading coefficient. The number of x-intercepts is related to the degree. The maximum possible number of x-intercepts is related to the degree of the function. So we will talk about that shortly. Now, another term that might come up that you're not sure about is even function and odd function, and how we determine that is the method used below. So if we fill in f of negative x is equal to f of x, we'll use this function here. F of x is equal to x to the 6th minus 2x squared plus 3. So what we're going to do is just plug in negative x in all the x values to see what happens. So we plug in negative x to the power of 6, of course, is positive x to the 6th. Negative 2 times negative x squared. Negative x squared, don't forget to follow BEDMAS, so brackets exponents first. Negative x squared is, of course, positive x times negative 2, negative 2x squared plus 3. Now, if you get to the end of this and you are able to produce the exact same function that you started with, which we did, then we say that the function is even. You can also test if a function is odd by doing a similar test, except the result that you're looking for is that the resulting polynomial is equal to negative f of x. So again, we just plug in those negative x values. We're going to use a different polynomial here, x to the 5th minus 2x cubed. And you just plug in those values. So negative x to the 5th is negative x to the 5th. And then, of course, this will give you negative x cubed times negative 2. We change it to positive 2x cubed. Now, we have a negative sign in the front here. We can factor that out of all the terms. So divide both terms by negative 1. And when you get to the end here, we get x to the 5th minus 2x to the 3rd, and our negative sign on the outside, which produces our negative f of x function. And we can say that this function is odd. So that's the way that you figure out if you're being asked for that. We want to be able to identify whether functions are polynomial or not, so that we're able to graph them and use their characteristics to help us find the answers to our questions. So of these two, there's an explanation given A through D here. Of these 4 given, these 2 are the only ones that are polynomial functions, and I just highlighted the degree, the leading coefficient, and whether or not there was a constant term annotated by CT there. So you can find those results and a little explanation given underneath as to why or why not it's a polynomial function. There's just several more examples here. So the first one is not a polynomial function. The second one, the degree, I wanted to point out a trick that happens in these questions sometimes, which is that they won't be written in descending order in terms of exponent power. If that happens, feel free to rewrite your formula. It's not always necessary, but if you're having trouble seeing the clarity of the question that you're being asked, then please do this. It will help you to divide polynomials as well as figure out what is the degree, etc. So here the degree is 5 because of that exponent. Our leading coefficient is -2 and our constant term is 4. Very similarly here, degree of 4, leading coefficient of -4 and constant term of +3. And this one is not because x to the 1/2 is a fraction. Our polynomial functions have some characteristics to them that are given by the degree. So the degree of the graph kind of determines the shape. So you can see here there's 6 examples from degree 0, which is just a straight line, all the way up to a quintic function or degree of 5. Now in our linear functions, this is a straight line, but not just on one specific axis. It'll have a rise over run or slope and sometimes a y-intercept. So when we have our function, we want to look at what is the end behavior of that, which direction does it go positive or negative in. Now, of course, if you have a positive function, it's typically going to increase in quadrant 1 and decrease in quadrant 3. If the slope was -2, then of course it would be the opposite. So just keep that in mind. Now, the same thing here with the parabola. We have a positive first coefficient of our graph, so that's telling us that direction. Remember when we were doing the transformations, that's the value of a. So if a is negative, it has to be pointing up. So because it's a parabola, it's going to be going up over the x-axis towards positive infinity. And typically parabolas, when we have them, they have 2 x-intercepts. Notice the correlation between the degree and the number of x-intercepts. That's something to keep in mind as you do these problems. Now it gets a little tricky in the bottom because you may not have seen these functions before, but the rules are much the same. We have a degree 3 cubic function. So if a cubic function is positive in our leading coefficient, then it's going to go, the end behavior will be positive in quadrant 1 and negative in quadrant 3. If that leading coefficient was negative, it would be increasing here and decreasing here instead. And you can see it's got 3 x-intercepts, so it loops up over top, down, and then back up. So 1, 2, 3. There's the quadratic equation. It's got this general shape with 4 x-intercepts, and then the quintic equation, which has this general shape, and it's got 5 x-intercepts. Notice something similar between the degree 4 and the degree 2. They're kind of parabola-esque, both of them. So the tails of those graphs will be going off into the same quadrant, either positive y or negative y at the end of your question, whereas the odd number graphs, odd degree graphs, they typically end in opposite quadrants from each other. As you're doing your problems throughout this unit, you can refer back to this page to give you reference characteristics for what your graph should look like when you plot it out. On the back side of that page, I gave some key ideas from the textbook just to give you a better understanding of what a polynomial function is and some review of some of the main points there, so you can read over that independently. And then beyond that, you have some practice questions related to this topic.